Hello and welcome back, everyone. I hope you've all enjoyed the lightning talks and the poster sessions that we've had lined up for you throughout the day. And now, last but not least, it is my great honor to introduce our keynote speaker for the first ever virtual DIR. His name is Thorsten Joachims. He's a professor at Cornell University, and he has been for the last 19 years. He has a long history in the broad fields of information retrieval and machine learning, and his work has had numerous awards that I will not be summing up in the interest of time. The title of his talk is Fair Ranking with Biased Data. It's a topic I believe is increasingly relevant in our field. So please join me in welcoming Thorsten. And Thorsten, the floor is now yours.
Thank you very much, Olivier, for the nice introduction. Also, thank you very much for the invitation to speak here. Would have, of course, be much nicer if I could actually be there in person, but this is as good as it gets these days. So what I want to do in this talk is step back a little bit and think about, what are the goals of some of the retrieval systems that we have built. And I would argue that as a field, we've been incredibly successful in getting these systems from, where they were originally conceived, like a library setting, to mediating whole sectors of our economy. So if I think about ranking systems and where we use them these days, I'm thinking about search engines. You type in a query, you get results. I'm thinking about retailers like Etsy here, where you can purchase products. I'm thinking about the many kind of media streaming services that use rankings and machine learning in particular to optimize these rankings so that you can find content that you're interested in. And I would argue that much of the news and information we consume these days is moderated through the rankings and through the ranking algorithms we built as a community. So I would say we've had a lot of impact, and we've had a lot of real-world impact. But I think with that impact comes responsibility, and also comes that we had somewhat of a drift in mission, right? And that the systems we originally conceived for a library system, for a library setting where people wanted to find books in a library, are now being used in settings that are way more complex, and where you have many more stakeholders that are involved in the use of these systems and the creation of the content. So what is it actually that, if I look at the majority of papers about ranking and about specifically about machine learning and learning these ranking functions, what do these systems actually do and what do they optimize? I would argue that the majority of papers aim to maximize the utility of the rankings to the user. And I think that's rooted in the tradition of the field, especially going back to where these systems come from. We wanted to help people find the books in the library, or help analysts find the content that they needed in the most efficient way. So, and I think this goal of maximizing utility of the rankings to the user is maybe best exemplified in the probability ranking principle and the paper of Robertson from 1977, which pointed out that if we want to maximize utility of the rankings to the user, basically for most reasonable measures of utility, what it means a ranking to be useful to a user, we should rank the documents by their probability of relevance. And that maximizes, almost for any measure of quality, that maximizes the utility to the users. And I think we've taken this as an axiom, and that's often what, if we train ranking systems using machine learning, or if we design ranking systems using also by hand, this is what we try to achieve. But is that really the only goal that we have when we use rankings outside of a traditional setting? but we use them in retail or in news or in settings like that. So let me give you a couple of examples that argue that we actually have to think more broadly in the policies that we use to design rankings. So, for example, here's a query that I recently had. I wanted to get a new table for my home office, and I was looking for these metal table legs on Etsy. And eventually, I typed in this query, and I actually bought metal table legs that look very much like those. So that ranking provided utility to me as the user of the system. But of course, there's also the other side. There are the sellers, right? Etsy is a marketplace where sellers can put up their products to get purchased. So by kind of presenting a certain ranking, the system had an influence on which sellers eventually make revenue, right? If something doesn't get shown, it can't actually be purchased. So there's utility to the users, but there's also utility to the other side of the market, which is utility to the items or the sellers behind the items. Or think about music streaming. So this is my Spotify account. It provides utility to me, or even more my kids who've taken over my Spotify account. I also work for Amazon Music, so actually personally I use Amazon Music. They find something that they enjoy, but there's also, of course, the streaming revenue that goes to the artists, right? But what gets presented here is more likely to get streamed, and whenever something gets streamed, an artist actually makes money. And maybe the final example is, all of the conferences that we organize. If we wanted to have, and some of them are getting very big. So like the NeurIPS conference has thousands of papers in it, and it becomes difficult to even find the papers that we're interested in. So having like a recommendation and ranking system would certainly be useful to me as somebody who wants to reach papers to the user. But of course, there's also a utility to the papers, to the items, or the writers behind the papers, because they want to get their voice out. They want to get their papers read. They want to have impact. And that, again, has very tangible utility to them that eventually they will end up getting tenure or not, right? So I think all of these examples highlight that in many applications, really these ranking systems are the moderator of a two-sided market, and they kind of set the rules for the market. So now, I still believe we want to maximize utility to the users, but what about the other side of the market, right? What would we want to guarantee to them? And I would argue that we want to be fair to the items, right? To the sellers or to the artists, right? And there's been a lot of contention actually from that side that sellers did feel that they were treated fairly. Now, do we actually have to actively do something about this, right? Would it actually suffice if we got even better at like implementing the probability ranking principle? If we actually maximize utility to the users, does that automatically somehow transfer over and give us fair results to the items? And let me go through a couple of examples to illustrate why that may not be true. So here is a mocked up example for a resume search system. So an employer can go into the system and can search resumes based on a query. So this employer is looking for a software engineer, and our system presents this ranking. And let's say our system is really actually very good at estimating the probability that that person will be invited for an interview by an employer that's by a random employer that's coming in and having this query. And let's say these numbers are 100% accurate. So system ranks by these numbers, and is that ranking fair? Well, Adam has a 55.99% probability of getting an interview. And if you go down the list, there's actually a lot of qualified candidates, right? They have almost the same probability of getting an interview. And you could argue that they're basically equally good. But what our system does is it actually creates a big disparity in how much exposure they're getting. You know, Adam, yes, has the highest probability of interview, gets put into position 1, probably gets a lot of visibility this way, a lot of exposure, and a lot of interview invitations this way. And, you know, somebody ranked in position 100, being almost, you know, having an almost equally high probability of interview, probably doesn't get discovered by anybody. So what the probability ranking principle does is it actually creates a kind of winner takes all dynamic that, you know, if you just epsilon better than somebody else, that translates in a potentially much higher kind of differential in exposure than this epsilon may warrant. Now, in this example, you know, if you look at this, you know, it's actually that all of the women or the people with stereotypically female names are actually ranked low, and all the men are ranked high. And it's not because women are less qualified to be software engineers here. It actually turns out that maybe there's like this 2% of the employers that that discriminate against women and that just don't invite women for software engineering interviews. And it would be very hard for us to figure this out. Now, what does our ranking system do here? It actually really amplifies this bias that our employers have, right? So this 2% of employers now have a huge influence on where the women get ranked. And that, in this way, actually our ranking system amplifies existing biases in the data and makes them even worse. And that's clearly something that we don't want to do. So ranking by just the kind of probability ranking principle does not appear to be fair when we talk about this kind of job application setting. Let me give you another example. It's the same numbers, but now it's like a music recommendation system where the system is recommending artists to me. And the probability that we're ranking by is the probability that I will enjoy this artist. And again, let's say this is, you know, this is an accurate estimate of the probability. So now there's, let's say there's no issue with gender or other groups. But what's going to happen if we do this? Well, A1 is definitely going to be discovered, right? It's going to get a lot of attention. And is probably also going to make a lot of streaming revenue from this. And so A1 will get even more popular and, you know, make more streaming revenue, will be ranked highly. So again, we have these rich get richer dynamics happening here that we may not want in our marketplace. In particular, like the artist 100 was ranked at position 100 here. Chance that I enjoy this artist is almost equally high, right? But that artist didn't really have a chance of getting discovered. And what will happen over time is that my market, or the number of artists that are actually participating in my platform, will shrink, right? There will be a few superstars, and everybody else is going to go out of business, right? They're not going to make enough streaming revenue to actually make a living. And so what's going to happen over time is my market will shrink, and there's going to be less good music available. And that's not in anybody's interest, right? That's not in the interest of the platform, that's not in the interest of the artist, and that's not in the interest of the users either. So again, if you think about just ranking by the probability ranking principle, it may have downstream consequences that we don't actually want for the health of our platform. And the final example may be around news. So let's say we have two news providers, the Times and the Review, one being more liberal, one being more conservative. And again, the probabilities of read are exactly correct. Ranking by the probability ranking principle will, and let's say we have a slightly more Times readers, slightly more liberal readers than conservative readers, but only by an epsilon, right? Probability ranking principle will put all of the Times articles first, all the liberal articles, and all the Review articles way down there. And rightfully, the conservative readers that want to see Review articles are going to say that that platform is biased against them, and they will probably not keep coming back. Again, that's not in the interest of the platform, and that's also not in the interest of the users. So in all of these cases, we saw that just kind of optimizing utility to one side of the market, to the user, does not automatically guarantee that kind of the other side of the market is served in a fair way, or kind of long term, we have a desirable outcome. You know, people will drop out, for example. So that argues that we actually have to do something, right? It's not, we can't just keep optimizing, you know, DCG or some other measure of utility to the users in these two-sided market applications of ranking. So, and I would argue that what we really need to ensure is we need to, well, keep having high utility to users, but we also need to have some kind of control, which you could call fairness, to the items. And if we want to ensure fairness to the items, and in particular a fairness of exposure, that's what it was all about, right? Who gets seen by the users and who does not. We want to allocate this scarce resource of exposure in a fair way in these systems. And there are two aspects to it. There are endogenous factors to it, and they are really about our policy of, you know, if we know everything about, you know, if you know all of the relevances, how do we actually compute a ranking based on that? And what are our principles behind this? And that has to satisfy, that helps us satisfy maybe legal requirements against regarding discrimination. But it also helps us kind of shape the marketplace that we have. And in particular, people at Spotify have talked about these superstar economics that they would like to avoid. They actually want to kind of have a broad population of artists that can actually make a living off their platform. And then there are exogenous factors that are all of the biases that kind of come with our data and that we need to take care of. So let's start with the endogenous factors. So let's say we know everything, we know all the relevances. What is actually the ranking that we should present? Or how can we constrain the set of rankings that we want? So I've talked a lot about exposure, right? That we want to, you know, exposure should be allocated in a fair way among the items, right? That's what we want to guarantee to this other side of the market. So let's define what we could actually kind of, what we mean by exposure. And this is the very simplest model that you can think of. So in this model, it's the position-based model. You simply say that, you know, an item at position 1 has a probability E1 of being seen by the user. In position 2, it has a probability E2. In position 3, E3, all the way, you know, down the ranking. And if you then say, you know, how much exposure does a group get, a group of items? So let's say, how much exposure do the women get for this query for software engineer, or how much exposure do the items that a particular seller offers get in your marketplace? You just sum the exposures that these items have, or get for a particular query. Now, these are just kind of fixed numbers, right? we have one number for each position. That's the kind of beauty and simplicity of the position-based model. You can argue that there's certainly you can improve on this, but that's the simplest model you can think of. How do you get these numbers? How do you actually estimate how much exposure does an item get in position number 3? There's actually, I mean, you could do eye tracking, and we've done that. But there's actually much smarter ways where you don't have to strap people into an eye tracker. And you can do these little kind of well-designed interventions where you basically swap results sometimes. And from these interventions, you can actually estimate like a differential of exposure, like that something in position 3 only gets 1/5 of the exposure from what you have in position 1. And there are these techniques about like intervention harvesting that you can use to actually get very accurate estimates of these numbers. And you don't actually have to put people into eye trackers or even invite them into a lab. You can do all of this remotely. So let's stick with this position-based model. One probability of observing the result at a particular position for each position. So how would we then define fairness? In some applications, we may define fairness as, like maybe in the job applications example, we may just say have some demographic parity type of constraint that says women and men have to get equal exposure. But in other applications, like when we're ranking artists in a streaming service, clearly we don't want to guarantee that every artist gets the same amount of exposure. Some are just bad, right? We don't, so we want to make exposure kind of depending on relevance or depending on merit of that item. And so what we could, for example, say is that if we have two groups, and the groups, maybe the tracks of one artist, that the amount of exposure that these items get should be proportional to their relevance. So that if there's an epsilon difference in relevance, that only translates into an epsilon difference in exposure, not into a potentially huge difference in exposure that we could get in the probability ranking principle if you are naive about it. You can make it proportional, you can make it some other function that's not a linear relationship, right? But that you're actually fixing the amount of exposure explicitly to the merit, to the relevance of the item. You can guarantee this per query, and say that, for every query, we want to have that every item gets exposure proportional to their merit, to their relevance. Or you can just kind of relax this a little bit and amortize it across multiple queries, where you're saying, okay, just kind of on average across all queries, the exposure needs to be kind of proportional or some other function of the relevance. So these are explicit constraints that we may want to put onto our ranking system. So, and then disparity is a quantity. It's like a quantification how much these constraints are violated. And I don't want to go into much detail of how you could measure the violation of constraints. Simplest case would be just to take like the squared error or something like that. So a disparity is something that we want to minimize. And that, a small disparity would guarantee fairness of exposure. Now, how do we actually construct ranking policies that could possibly achieve this kind of fairness of exposure? Because if we just present deterministic rankings, we're kind of stuck with if you put something in position 1, it gets that amount of exposure, and position 2, it gets that amount of exposure. But it's all discrete, and we can't like optimize this very well. But we don't actually have to have deterministic ranking policies. It's actually much easier to deal with stochastic ranking policies, where we're actually drawing which ranking to present from a distribution of rankings. And I've given a little example here so maybe our ranking policy for a particular query X, like picks from these three rankings, picks the first ranking with probability 52%, the second ranking was probability 23%, this one was 20%, this one was 5%. And now by kind of picking the right rankings and by adapting the probabilities, we can really, in a fine-grained way, kind of say how often does each item occur in each position. In particular, we can now take like the expected utility that an item has over this distribution of rankings. We can talk about the expected exposure that an item has over this distribution of rankings. So for example, the item A has now probability 52 plus 20%, so that's 72% of being in position 1. It has probability 23% in being position 2, and it has probability 5% in being position number 3, and 0 for everything else. And that gives us a very fine-grained control about, what is the number of people, what's the probability of this item being seen, right? And now our optimization problem, if you want to find policies, becomes, picking this base set of rankings, and then kind of adapting these probabilities. So that gives us an expected utility that we can optimize. And it gives expectation over these rankings presented by the policy and an expected exposure. So now we have everything that we need to actually formulate the ranking problem, or a ranking problem under fairness constraints. So just like before, we want to find a ranking policy that maximizes utility to the users in expectation over the queries. So this is an argmax over ranking policies now, and these are stochastic ranking policies, these probability distributions, subject to the constraint that we want our disparity to be less than some quantity delta. We could say set this to 0, but whenever you have a constraint on an optimization problem, that means there's a trade-off here, right? If we make this delta, if we kind of enforce fairness a lot, this can decrease utility to the users. So there's a trade-off between delta and utility here. But in general, we can have a constraint that says we want our utility, our disparity, our unfairness to be constrained. How do we solve this? Well, you can introduce a Lagrange multiplier for this constraint. And then instead of optimizing this constraint optimization problem, you can just translate it into this unconstrained optimization problem with this Lagrange multiplier lambda. And instead of actually maximizing over this, minimizing over this Lagrange multiplier as well, you can just pick a Lagrange multiplier and then pick the delta in hindsight for which this is optimal. And so this basically gives you a formulation where this lambda here gives you a trade-off between how much emphasis you put on utility and how much emphasis you're putting on fairness. So that is one approach to now actually defining policies that kind of take care of the endogenous aspects of unfairness. You can implement these legal requirements that you have, or you can implement what you want your marketplace dynamics to be, right? And you can put additional constraints on there. You can also use it to kind of discourage spam and polarization this way, right? If you, for example, think about that spam really pays right now under the probability ranking principle. If you just become epsilon better than everybody else, that gives you a huge benefit. So spamming, or search engine optimization, actually is really profitable from this perspective. If an epsilon improvement in relevance only gave you an epsilon improvement in exposure, spam may, or search engine optimization would actually not pay off that much anymore. So there are lots of things that you can actually kind of steer through having these additional disparity constraints on your ranking policy. So, but for now, we had always assumed that we actually know what the relevances are, right? But we, of course, in practice, we don't, right? We actually need to estimate them. So how do we now come up with estimates that we can then stick into our ranking policies that we've just defined and that we would like to optimize? And now we're getting to these exogenous factors that can kind of influence the fairness of our system. And there are lots of biases that come with our data. There's position bias, trust bias, potentially biased features. There's stereotypes, like in the drop placement examples. And they're very difficult to deal with. And they get you very deep into causal reasoning and causal inference. Let me talk about the simplest one, that I think we actually do have a good handle on. And that's the problem of position bias. Because that's actually a bias we, as the designers of the search engine policy, control. So what do I mean with this? So what we typically have when we are running a search engine or when we're running an e-commerce platform or recommender system is we have log data. And in this log data, we presented this ranking, and then we get, maybe clicks or plays or interviews or something like that. We get feedback on some of the items. So, but of course, that deployed ranker that collects the data biases the data, the click data that we get or the feedback data that we get, right? Whatever we put into position 1 is probably going to get the most feedback. And if you put something into position 1000, even if it's great, we're going to get very little positive feedback on that. So we are biasing our own data that we would want to learn from in the future. How do we deal with this bias? Can we get rid of this bias? So what's the problem here? So let's try and narrow down the problem. Let's again go back to a very simple model of how people behave when they give feedback. And it relates to, again, the position-based model again. So if we see a click on something, let's say a click on this item in the 3rd position, then 2 things must have happened. The user must have seen it, and the user must have found it to be relevant. Whatever your measure of relevance is, a click is probably not a good one. Maybe you want to do something, a long click, or you actually verified interview or purchase, whatever it is, right? But these 2 things have to come together, right? The user has, if there is a click, the user must have seen it and found it relevant. And vice versa. We can, I think, safely assume if the user sees something and finds it relevant, that the user will give us positive feedback on it. Let's say a click for simplicity. That's actually pretty straightforward. But where the bias comes in is for the items that don't get clicked, right? And there's an ambiguity. There are 2 possible reasons for this, right? 2 possible causes. One cause is the user didn't see it. The other cause is the user didn't find it relevant. And we can't really tell it apart, right? At least not deterministically, right? So how can we tease apart how much of kind of the missing clicks are based on not seeing something versus it not being relevant? And for that, we have to understand the observation mechanism. It's often called the assignment mechanism in the causal inference literature. So, and there we can go back to our exposure model that we had before and think about these exposure probabilities as propensities of observation. In particular, what we basically said was that something at position 3 has, let's say, a probability of 0.5 of being seen, and position 4 of 0.2, and so on, right? And position 1 of 1.0. That were our exposures that we had before, that we said, that I argued we can estimate well. These are also the probabilities of observations in the model on the previous slide, right? And it turns out that we don't actually need to know for any particular query whether a user observed the item or not. We only need to know the probability of observation to be able to debias the click data. And the technique one technique for doing this is called inverse propensity score weighting. So, and it lets you, for example, if you want to estimate DCG of a ranking based on clicks alone, it lets you get an unbiased estimate of DCG or many other performance metrics, even though you only have clicks under this exposure model. So why is that possible? And it's actually pretty simple. If you know that, if something relevant is in position 3, if you know that you see this kind of positive feedback signal for position 3 only half of the time, basically every time you do see it, you upweight it by the inverse of that, by a factor of 2. And if you know that something in this position down here, you see a positive signal only 20% of the time, every time you do see it, you upweight it by a factor of 5. This upweighting means that in expectation, you're kind of seeing it the right amount of time, and it's not confounded by where it was placed. So there's actually, it's really just a kind of 3-line proof to show that under this exposure model, you get an unbiased estimate of, say, DCG or whatever your utility metric is, by doing this inverse propensity score weighting. And similarly, you can do things like estimate the relevance of a group using these inverse propensity score estimates as well. So this gives you a way of getting unbiased estimates. Unbiased from a position bias perspective. It only corrects for position bias, not for some of the other biases that I had before. But at least that bias, which is, I think, a really big component in many ranking systems, you can get rid of. So now we have everything together. We can take our objective that we want to optimize, some trade-off between utility and unfairness disparity, and we can plug these unbiased estimators into our training objective. So this becomes an unbiased training objective. In expectation, this optimizes the right thing. The last thing that we need to think about is, how do we actually optimize over the space of ranking policies? And that's a combinatorial object, right? There's like an exponential number of different rankings that I can present. And so these distribution over rankings here, there's kind of an exponential space that we would need to optimize over. That seems daunting, but you can actually use techniques from reinforcement learning, in particular off-policy gradient techniques, to do stochastic gradient descent on this objective, even though you have an exponential sized policy space here. And what we're doing here is we're saying we're constraining the space of policies to be Plackett-Lutscher ranking distributions. And these are really easy to sample from. You just basically, you have your scores. You have a score for every item, just like you have in a normal ranking system, but you don't sort by them deterministically. What you do is, for the first position, you present you draw an item proportional to the scores, whereas the probability proportional to the scores. Place that into position 1. Now take it out of consideration, and then draw the next item proportional to the scores for position 2, and so on. And that's how we construct stochastic ranking. So it's really easy to sample from this, and just being able to sample, you can actually compute a stochastic gradient for this objective, and then optimize it. And again, I'm sweeping a lot under the rug here, but that is actually tractable. All right, so how well does that actually work? Can you put everything together and actually, verify this experimentally? So in the first experiment here, we took the Microsoft Learning to Rank corpus, and we kind of artificially created two groups. We just picked one of the features. I don't actually remember which one it was, and said, let's be fair to, there's one group being everybody who had that feature to be low, and the other group is everybody who had that feature to be high. And we want to enforce fair exposure to these two groups in this amortized exposure allocation way. And we used this Plackett-Lutzer ranker, and we just had a linear scorer, basically a linear ranker that just had a weight on each feature. What this plot shows is unfairness on this axis, so lower is better, and DCG, so utility, on this axis, so higher is better. So you want to be down in this corner, right? That's fair and high utility. And what this experiment evaluates is whether, despite the fact that we have this biased click data, if we do this inverse propensity score correction, do we actually converge to a solution that is just as good as if we had unbiased data? So this full info line here is if we actually train that fair objective with the ground truth labels. And then you get a trade-off. So that if you sweep that lambda parameter, that trade-offs between fairness and utility to the user, you get this kind of a curve. So if you crank up the lambda a little bit, that really decreases your unfairness. But if you want to get it perfectly down to zero, you actually have to pay quite a lot at some point you have to pay quite a lot in terms of utility to the user. But here you can see, if you now use the biased click data instead of this perfect data, if you use enough of it, so this is 4,000 clicks, this is 12,000 clicks, 36,000 clicks, 120,000 clicks, eventually you do converge to the true kind of full information objective. So basically, if you have enough data and your model is correct, the click data kind of gets rid of, you can get rid of the bias in the click data. So that kind of verifies that argument around exogenous bias. Let's also look at the kind of endogenous component. And let's compare this type of constraining the set of ranking policies to be fair to other proposed methods for enforcing kind of fairness to the items. So the first point of comparison is probably the most naive one, is what's called group blind. So there was this feature that told us which group the item was in, and we just took it out of the data set and hoped for the best. Well, that was it's of course very naive. There's no reason why this should give you a fair exposure. So, and you can see here that's the same type of plot. You don't achieve fairness this way. There's also other techniques that basically require you to first learn an unbiased estimate of all the relevances, and then kind of post-process it to be fair. And that's different from the technique that I introduced here, right? There we do both the learning as well as being fair. We do that as one optimization. So if you do post-processing, the problem is that that even if you try to debias the clicks, your estimated relevances, you're kind of having a two-step approach. And what you do in the first step, this kind of trying to estimate relevances, does not necessarily do the right thing or optimize the right criterion for what you would want to do in the second step. So like these post-processing methods can fall into the trap that you're actually kind of working with the wrong inputs. And so, even if you try to enforce it more strongly, it doesn't get you a more fair solution because it doesn't work on the right data. And then there's these two algorithms here. That's two variants of what I proposed here. And there's the linear version, that's the blue curve, and there's a deep learning score. There's a deep network behind it. And both actually manage to get down to 0 unfairness here. And the deep learning model has more capacity, actually does a little bit better. All right, so these were the two aspects that I think in these two-sided markets we really need to think about. These endogenous factors, like how do we actually design the ranking policy, and the exogenous factors, how do we kind of try to deal with biases. And right now I've only dealt with the position bias. And there's lots of open questions of how do we actually deal with the other biases that could come up. So I think this by itself opens up a big space of research opportunities. But let me actually go even further, right? We're using these ranking systems in ever more complex settings. And I think the kind of the successes that we had in recommending movies and music, and people are trying to translate it to other settings as well. And in particular, recommending movies certainly has is important and has an impact. But we're starting to make rankings part of being very consequential decisions, like recommending jobs to people. And if you think about the settings there, this is a two-sided market as well. Like a job recommender, you have employers that have preferences over employees. And you have employees that have preferences over employers and jobs. And so we're applying these ranking systems not just to the kind of two-sided markets that I had so far in the talk, but we're also applying them to matching markets where two sides actually have preferences about each other. And that's different from like movies, right? People have preferences over movies, but movies don't have preferences over who consumes them, right? So, and once we go to these matching markets, in particular consequential decisions of which, what do we recommend, or what employers do we recommend to certain applicants, I would say that, so the rankings, even the ranking policies that are introduced so far, don't actually model this very well. Because everything becomes connected, right? The preferences of one applicant and one employer kind of influence everything else. If I recommend, so for example, we're faced with a conundrum of maybe applicant A really likes employer X, but we are pretty sure that employer X will not hire A. Should we actually show that employer to the applicant, right? Are we just wasting that applicant's time? The other thing is, what do we actually want to achieve? This is actually really very important for our economy, right? We have a certain social welfare that this matchings or this kind of recommendation system would present to our society. We want, as a society, to have people find jobs and employers find people, right? And the better we can match this, that we're optimizing a social welfare of, let's say, the number of actually matches that we can make, and the number of, minimize the number of people that are unemployed and minimize the number of open positions. And all of these different criteria are not necessarily fully aligned with each other. And how do we trade them off? How do we actually design rankings now that take all of this into account? I think these are fascinating open questions that we, I think, as a community need to deal with and get them right. So let me wrap up. I try to kind of think about more broadly what are interesting new questions for ranking systems. And I think a lot of the fairness questions were already discussed early in the day, and especially in the previous section. But I think there is a big research agenda as ranking systems now move to all of these additional applications, often with much more consequential decisions and much more complexity than just optimizing utility to the user. All right, thank you.
All right, a big thank you, Thorsten. This was a very inspiring keynote with a lot of food for thought. One first sort of more of an like sort of high level question that I have is when you are talking about like sort of the sort of concept of the exposure that an item gets needs to be sort of related to the sort of relevance of the item. Would you say that it also needs to be like the sort of other way around? Because one sort of impression is not necessarily the same as a sort of second impression. I mean, when you have a seller who is going to sell something, it might be that one impression is actually much more valuable to the right person than 1,000 times showing this to the wrong person who won't buy it anyway. So
Right.
Is that something that you also need to sort of take into account? And do you have any thoughts on this?
Yeah, yeah, I fully agree. I mean, in a way, this is still simplistic, what we're optimizing here. Yeah, as you're saying, right? An impression is counted as an impression. And in particular, like some of these amortized criteria that I had here, there is a potential for the system to actually, again, have unintended, optimize this criterion, but still have unintended effects. So, for example, what could happen is, so maybe you enforce that men and women get the same exposure in a job application system. But then what the system does is, it presents for the query doctor, that's where the men get the exposure, and nurse, that's where the women get the exposure, right? There's clearly an issue that, there's still a stereotype in there, and that even though the exposure is the same, that maybe the exposure isn't equally valuable across different queries. You're also pointing out, right? Maybe it's not equally valuable to to have a second exposure to the same person, right? That's all still kind of simplified away. So I think there's a lot more room to actually model this much more closely. And I think this will really just basically first steps for doing that.
Right. Okay. Thanks. We have a few new questions in the chat. I will read them to you. The first one is by Sami Kenisi, and he asked whether it is sort of his main question is whether it is enough to sort of eliminate bias in one sort of iteration, whether that is going to solve bias in future iterations of the recommender system.
Right. There's interesting long-term dynamics. So for the selection biases that I talked about here, where it's basically the position bias, we're actually in the nice position that you're basically debiasing it in a way that there are no dynamic effects. But I think that's a very special case. And there's certainly kind of second order effects that are ignored by that. So for example, if you look at the psychology of how people appreciate music, then there are these learning effects. So you for somebody to actually really, enjoyment of music actually grows the more often you have listened to a piece. So if and I think that often happens, that there is this dynamic that hits are created, right? You hear it over and over again and enjoy it more and more over time. These kind of second order effects of that actually the utility or the relevance of an item changes through being exposed, right, are currently not modeled here. And so there's definitely some dynamics here that we would want to kind of be careful about modeling as well. And I think that's, again, it's a very kind of domain specific kind of question of what are the additional kind of dynamic effects that we may have. There was also a very interesting ICML paper, won the Best Paper Awards, I think 2 years ago, about credit scores. If you try to kind of correct and maybe do an intervention for kind of debiasing credit scores, that it actually kind of dynamically makes the group of people that you wanted to be fair to, that actually makes them worse off. So you really, it's a very complicated modeling problem that you have to think about when you're designing these constraints.
Right. Okay. Okay. That's super interesting. We have a few more questions. The next one is by Zoltan Slavik. He asks, isn't the click dependent not only on being observed and found relevant, but also what else is already been seen? So the items that are higher in the ranking.
Right. So again, simplest model you can think of. You could think about, so here it's, you're basically assuming that these numbers are constant, right? And they're constant across all queries, and that they're independent of what's ahead of it. Now, there's two aspects to answering this question. The first one is, if these numbers were different for different queries, would IPS weighting still work? And the answer to that is yes. That's great. Now, that then raises the question of maybe there are better models of kind of trying to, figuring out, maybe depending on a particular query, these numbers should be different, right? Maybe if you have an informational query, people go further down, and so maybe that curve should be not dropping off that fast. These numbers shouldn't be dropping off that fast. Maybe for a more navigational query, they should be dropping off faster, right? In addition, as you said in the query, in the question, maybe if something relevant is in position 2, that affects the kind of how likely people are going to go to position number 3, right? All of these things, in principle, should be modeled. And they, there's a lot of room for improving these propensity models, I believe. But the good news is that IPS weighting could make use of all of these improved models. So it's an interesting area of research. There's actually one paper that kind of tried to implement kind of a cascade style propensity model for this. And that would be a first step, for example, taking dependencies into account.
Right. Okay. We have time for maybe one final question. There is a question being asked by Harry Osterhaas, where he asks whether you think that having these whether having these stochastic rankings can have negative effects on user experience. For example, users that are like sort of a bit confused that they are not sort of like finding a search result, and how you would deal with that.
Yeah. First, congratulations again, Harry, for being for getting your PhD. Excellent defense. That's a very good point. And the way that I would probably implement, if this was a real system, an operational system, but that I would implement the stochasticity of a ranking policy, is to actually not being stochastic per impression, but it being stochastic per user or customer. So, for example, that you would actually do basically that every time any individual person would always get the same ranking. And you could implement that, for example, by taking a hash of the user ID and actually randomizing based on that hash. so that every time the user comes back, it actually sees exactly the same query. Then the randomness would be across users, but that would be sufficient as well.
Right. Okay. Thank you. I think we are going to have to wrap up here. There are a few more questions in the chat, but yeah, I'm sorry. We have to stop somewhere. So once again, a big thank you to you, Thorsten. I'm sure people are all joining me in clapping at home now. And then I will now give the floor to Jan, who will wrap up our first ever virtual DIR.
Yeah, thank you very much, Olivier.
Yes, thank you again, Thorsten. It was really nice, really interesting. So we have arrived at the end of our workshop, almost at the end of our workshop. So we are super happy to see that people are still around. So thank you for joining us the whole day long. It's been very nice to see all of you engage during both the lightning sessions and during the posters. So thank you for that. We're also very happy with the presentation themselves. I think I speak for all of the organizers when I say that, you know, the quality was super high, and everyone brought some really interesting research to our workshop day. So this is the program. You just managed to go through with us together. So we want to say one more big thank you before we move on to the last block, which is socials, to our sponsors. So thank you very much, Fumel. Thank you very much, DPG Media as well. Thank you to Bull for sponsoring. Thank you to Text Kernel. And thank you to Zeta Alpha. It's been really nice to have you on board for this and make everything much easier to implement. So, of course, thank you also to so many other people. I cannot name everyone, but first of all, I definitely want to not forget to thank our chair. So thank you, Bart, Susan, and Christina for really leading smoothly, guiding us smoothly through these lightning sessions. And then, of course, here's the list of people who contribute to organizing today. Thank you very much to Liam, to Joey, to Robin, Olivier, and also to Bart. We are not done, so I want to emphasize that. A question, there's an important question we need to ask, and it is, I don't think there's a team yet that has volunteered or committed to organizing next year's DIR. So if you are interested, please contact us. You can contact us right now through our website, or you can send an email to this email address. We will be keeping an eye on that. It's been a lot of fun for us, so we definitely encourage you to give it a shot. And last but not least, the day is not just over yet. The gather room we have will stay open. We will have it open for a bit longer, plenty of time to go and chat to each other, discuss the posters you've seen, discuss the keynote, ask each other a few more questions, and also feel free to grab a drink, just socialize. That's often one of the more important parts of the workshop as well. So we want to make sure you also get to experience that. And with that, I think we are through our thank you notes and our closing session. Hope to see you in Gather after this, and thank you again for all being here. And hope to see you also next year. Who knows, perhaps in person.